Resistivity and resistance. We've been talking about resistors and resistance. Now we're going to go in some more detail and explain exactly what's going on. Let's go back to our water analogy to explain how the wire in a circuit can affect the current. And remember what the circuit is. You've got a battery, then you have a wire, and you have maybe like a light bulb here, and it goes back to the battery. If the wire is like a pipe and current is like water that flows through the pipe, that's a couple dots there. Let's say we have pipes with water in them. What could we do to the pipes to change the speed of the water, which is analogous to the current in the circuit? Well, we can do a couple things. We can change the cross-sectional area of the pipe. Right? If we make the cross-sectional area bigger, there's more room for water to flow, so that will decrease its resistance. We can also change the length of the pipe. If we increase the length, that will increase the time it takes for the water to get to the end of its trip. We mentioned earlier that every conductor conducts electric charge to a greater or lesser extent. The last example that we used on water, the previous one, works for copper wire. If we decrease the length or increase the cross-sectional area, we increase the conductivity. Okay, more current can flow. Right? We showed increasing the length of water would be less current, so decreasing we'd have more current. Now we normally don't deal with conductivity, we deal with resistivity. That's the opposite. We represent that by rho, another Greek letter, and every material has a different resistivity and it depends on its atomic or molecular structure. Resistivity will also change with the temperature of the material. So if we combine what we know about cross-sectional area, which is A, the length of the wire or conductor, and the resistivity, and again, what can we change if we have a bunch of copper wire? We can't change the resistivity. That's always the same for copper, again, assuming it's at the right temperature. We can change how thick the wire is, the cross-sectional area, or how much of the wire we use. And then we can talk about resistance. Resistance will be rho L over A. Resistance is measured in ohms. Cross-sectional area, meters squared. I mean, wires aren't written like that. Typically they'd be millimeters squared, or if they're really big, centimeters squared. But you have to convert it to meters squared for it to work in our equations. Length measured in meters, and resistivity is ohm meters. Materials with a low resistivity are preferred for making conducting wires. Why? Well, we're going to want the maximum current for a given voltage applied because we want to do a lot of work with it. So low resistivity means more of that energy goes into our vacuum cleaner or light bulb and less goes into heating the wire that connects them. That's just wasted energy from our point of view. So what is the resistance of a good conductor? Low. Low resistance means that electric charges are freer to move in the conductor. And here's a little spool of copper wire. And we have another simulation from PHET on resistance that is worth your while to check it out. Here's a table of some resistivities of common conductors. So what do you notice about that? Who's your best conductor? Silver. Then copper is a close second, then gold, and then you go all the way down to nichrome, which is not a very good conductor at all. So if silver is a better conductor than copper, why don't we use silver wiring? Well, a couple of reasons. One, it's vastly more expensive. Two, it corrodes more easily than copper. And three, it's not as malleable as copper. So copper is our choice for household wiring. For a time in the 1960s, they used aluminum. It's not as good, but it was cheaper. The problem is when you connected aluminum up to copper wiring, it didn't have a good connection there. The aluminum would oxidize, the connection would suffer, and you'd have sparks. And you don't really want to have sparks in the wall of your house. And there were some houses that caught fire because of this. So you're not allowed to have aluminum wiring anymore. It all has to be copper. And for people who did have aluminum wiring, there's special connectors that are made to connect them safely up to copper so you don't have those issues. But going forward, you build your houses using copper wire in the walls for the electricity.